Okay, so let's take a look at Zoltar Speaks. This is a lecture over how to predict the different types of chemical reactions. So, how do we predict the products? Okay, in the previous lecture, we learned how to predict the types. Now, we're going to take that a little step further and try to figure out how to predict what types of products are going to form. The quote we have: the best way to predict the future is to create it. So we're going to look at some of these. The learning of goals, learning objectives that we want is that students will understand how to predict the products of the 5 basic types of chemical reactions. So basically we're talking about our single replacement, double replacement, synthesis, decomposition, and combustion. We want to be able to predict what the products are. So if we put these two compounds together, what are the products going to be? Number 2, students will understand how the activity series is related to chemical reactivity. So we're going to try to figure out what the activity series is and how is it related to how reactive something is. Number 3, students will be able to use the activity series to predict if single replacement or oxidation reduction reactions actually occur. So we're going to look at, well, do all reactions happen? Just because we put two things together, is it going to happen? So we're going to try to figure out how we can predict if a single replacement reaction will occur. And lastly, students will understand when solids will precipitate out of solution in a double replacement reaction, or a precipitate reaction. What we're looking at here is we're trying to figure out, well, does it produce that precipitate? Does it produce that solid? And how can we know if it's going to do that in advance? So let's dive right in. It says, how do you know what type of reaction you are working with? Well, the first thing we have to do is we have to figure out what type we have. The main thing here is what you start with is key. So our reactants, the reactants of the chemical reaction will determine what type of reaction will occur. So basically what we start with will determine what we're going to finish with and what type of reaction we're going to have. Okay, so it's all about what we're starting with because that's all we have. How do you know what type of reaction you are working with? So how do we figure it out? Well, if we start with an element and an element, more than likely what's going to happen is we're going to have a synthesis reaction. And the synthesis reaction produces a compound. So an element plus an element will produce some type of compound. Okay, that's for synthesis. Looking at this one, if we just start with a single compound, we can assume that it's going to be a decomposition reaction, and the product will equal 2 single elements. So if we start with a compound, just a compound, then what we're normally going to end up with is an element plus an element. Okay, great example is water, H2O. It breaks up into hydrogen gas plus oxygen gas. Okay. If we have an element plus a compound, we're going to have a single replacement reaction. Okay, and the product will be another element, another compound. Again, remember that like replaces like. So metals replace metals and nonmetals replace nonmetals. And lastly, if we have a compound plus a compound, then we are going to have a double replacement reaction. And remember, they switch partners and produce a compound plus another compound. Okay, and then we have our combustion reaction. If we have some type of molecule and oxygen, then what we're going to assume is that it's going to produce CO2. If that molecule happens to have a carbon in it, it'll produce CO2 plus H2O. Okay, so if we have a molecule plus hydrogen, we're going to produce a combustion reaction, which is CO2 plus H2O. Okay. After you know what type, how can you write the products? So once we know what type of reaction we're going to have, we have to write the products of what we're going to have. So you follow the rules for that type of reaction. So for a synthesis reaction, we have an element plus an element. It's going to produce a compound. Normally, it's going to be an ionic compound. So what do we have to do for ionics? We have to crisscross. Okay, all compounds must have a balanced charge. So we have to crisscross them out to make sure that they're balanced. And then we want to write the formulas and check elements for diatomic. And the normal place where people like to mess up is in those diatomic molecules. We forget about Brinkelhoff, and so they'll write bromine and they'll forget to add that 2, which changes the formula, changes the equation completely. So those are some things that we need to look out for. Follow rules for that type. What does it produce? Make sure that we crisscross for those ionic compounds, and when we write the formulas and check the elements for diatomics, we always check for diatomics. So our first example, it says speculate on the products that could be produced when pure sodium, so we have pure sodium, which is Na, okay, is placed in pure water plus H2O. Okay, so when we're looking at this, we have an element plus right here we have water molecule, which it's more than an element put together. So what do you think is going to happen? Well, hydrogen has a unique property of having both metal characteristics and non-metal characteristics, meaning that in a molecule, it'll become ionized and it will give a lot of its electrons, give it one single electron to whatever it's bonded to, and it acts kind of like a metal. Well, here, remember, we always said when you look at water, think of water as H bonded to OH. So think of it this way. Well, sodium is going to come in and bump off that hydrogen. So I have hydrogen all by itself and then sodium bonded hydroxide. So hydrogen all by itself, we check, is it a part of Brinkelhoff? Remember, it's BRINCLHOF for the F, and then we see that yes, it is. It's right there. So instead of just writing hydrogen, we write H2. Okay. Plus now sodium, which is Na, is bonded to hydroxide, which is OH. It's an ionic compound. We need to crisscross. So sodium is going to have a positive 1 charge. Hydroxide is going to have that negative 1 charge. So we crisscross the 1s and we get NaOH. Okay. From here, we would go ahead and we would balance it out. Looking on at the next example, it says predict the possible products of the following chemical reaction. So we have potassium oxide plus our fluorine. So we have a compound plus fluorine, which is an element. Well, compound plus an element, we're going to have a single replacement reaction. So when we're looking at this, remember, like replaces like. So fluorine is a nonmetal. It's going to replace the nonmetal in potassium oxide. So that fluorine will replace that oxygen. So the oxygen's by itself. Is it a part of Brinkelhoff? Yes, it is. So it's O2 plus potassium, which is our K, is now bonded to our fluorine. Okay, so when we're looking at this, we check. We know that fluorine has a -1 oxidation number, and so does potassium. Switch spots, and we get KF for our potassium fluoride. Last example, it says predict the possible product for the chemical reaction. We have magnesium and oxygen, so an element plus an element. When we see that, synthesis. So it's magnesium bonded to oxygen in a compound. So anytime we bond this up, it's ionic. We need to crisscross, which magnesium is going to be our +2. Our oxygen is going to be our -2. So we crisscross the 2's, and they can be reduced down to, it's a 2-to-2 ratio. It can be reduced down to a 1-to-1 ratio, which is magnesium oxide.